Welcome back everyone to the next video in our series. Today we're going to look at electric circuits, and in particular the series circuit. So here you see in front of you I have a picture of a series circuit, but I'm going to take you directly over to the FET where I have this circuit in live action. So let me just explain very simply what we have, and then we're going to continue to the analysis together. Here we have a 24-volt battery, and it's pushing electrons through this wire. It meets the first light bulb that has a 2 ohm resistance. You see the electrons going up and through the wire. Connected by another wire to the next light bulb, 4 ohms. Then the electrons keep flowing to the third light bulb, which happens to be 6 ohms, and then we have a wire bringing it all the way back to the battery. So all circuits have to have a power source, a conducting path, and a load, at least one. A simple circuit would have had 1 light bulb, but this is a series circuit. So that means there's more than one electrical load on the circuit. We're going to now analyze a process. We're going to now use a process to help us analyze this circuit. It might seem very confusing, and what are all of the different calculations that can be done for this circuit? Well, let's take a look back at that original slide, and we'll see that there is a 1, 2, 3, 4-step process. So let's talk about what these steps are, and we're going to go through it in order. The first thing we want to do when we see a series circuit is find something called the equivalent resistance. The equivalent resistance is simply the sum of all of these resistors, and we look and see how does it act as if it was just one resistor. And that one resistor will let, in step 2, a total amount of current flow through. Now, step number 3 is a little trickier, but when we get to each light bulb, we have to find what's called the voltage drop. That's the energy spent by the battery in pushing an electron through these different light bulbs. Since these 3 light bulbs were purposely made to be of different values, you're going to learn that each light bulb requires a different amount of energy drawn from the battery to cross the bulb. And we're going to use an analogy like a toll bridge. You have to pay a toll to get across. So we're going to explain that in a moment. And then finally, how many watts of power are used in the whole circuit and at each element in the circuit. All right, let's get started with an example. Before we can start any problem for series circuits, we have to first get our reference table ready. So we're still back on the electricity page, but this time we're going to scroll down. We're going to need equation E5, which is the Ohm's law equation, and we're now going to need this series circuit group of equations. In the next video, we're going to be talking about parallel circuits, so I'm going to be using this side. But right now, I'm going to use the left side. And you can see I have a doodle diagram here. I have a battery, I have an ammeter, I have some voltmeters, I have resistances, and I'm basically modeling this circuit in the FET right here. Here it is live. And we're going to use 3 rules. So let's just talk about the rules. The first rule says that the total current is equal to the current in all of the elements of the circuit, 1, 2, and 3. Since there are no branches, all of the current has to flow through all of the pieces. Wonderful. The second rule here says that the voltage drop total is equal to the sum of the voltage drops of all the pieces. We're going to explain that in a lot of detail when I review the problem, but basically it means this. The energy that I get from the battery, I have to spend some of it here, here, and here. If I added that all back together, it gives me what I started with. And then, of course, the resistance of the total circuit is equal to the combined effect of the three resistors, here, here, and here. All right, let's get started on that problem. As you can see, I set this series circuit up so that it has a 24-volt battery, then a 2-ohm resistor light bulb, followed by a 4-ohm resistor light bulb, followed by a 6-ohm resistor light bulb. What is the first thing we have to do? In every series circuit, we have to calculate the total resistance. So let's take a look at an Excel template calculator that I created for this. So I have a 24-volt battery, a 2-ohm, a 4-ohm, and a 6-ohm resistor connected in series. The first rule says that I have to find the equivalent resistance of 2, 4, and 6 ohms respectively. And that, of course, equals 12 ohms. So in this circuit, this 24 volts has to push against a total of 12 ohms. There you go. That's the first step. Very easy. Let's move on to the next step. In step 2 of this problem, we want to know what the total current allowed to flow through the circuit is when we have a total energy storage pushing with 24 volts and being resisted by 12 ohms. And so this is a job for Ohm's law. I, current, equals V divided by R. Potential difference, or voltage, divided by resistance. This formula is exactly off the reference table, E5, and it's solved for I. Now, when we do the simple math, we get 24 volts divided by 12 ohms, and that gives us 2 amps. So this circuit allows 2 amps of current to flow through it. Let's move on to step 3. The next part of our computation involves us calculating the voltage drop, or the amount of energy used at each light bulb. Now let me just give you a little background on the word voltage drop. The reason why we call it voltage drop is because the total amount of voltage here, the energy that's stored in this battery, gets used. Some of it gets used here, which drops the total from the original. Then some more of it gets used here, which drops this available total some more. And the last bit of it gets used here, which drops it the final amount. Let's do the calculation together. So to find the voltage drop, all you have to do is use Ohm's law again. You see it's over here, I is V over R, but this time we're going to solve it for V, which is I times R. So that Ohm's law comes back again, and you're going to go to each piece. So you know it's I times R1, the first light bulb, I times R2 in the second light bulb, I times R3 in the third light bulb. Since we know that all of the current in all of the bulbs is 2 amps, 2 amps will be multiplied by the 2 ohms of the first light bulb, the 4 ohms of the second light bulb, and the 6 ohms of the third light bulb, respectively. So you get a voltage drop of 4 volts when you cross the first light bulb. That means out of the 24 available volts you started with, you've used 4 of them. So you've dropped the available energy by 4. Now you get to the second light bulb. And this second light bulb uses more energy because it has a higher resistance. So it's harder to push through it, so you have to use more energy. And then you get to the third light bulb. That was a 6 ohm resistor. That's even more of resistance, which requires more energy. Now here's a very interesting fact. If you were to add up the 3 voltage drops, you get back to the original 24. And that's actually the rule that is right here on the reference table. If you add the three up together, you get back to the starting point of what you had in your battery at the beginning when you started distributing energy. So before we move on, let's just verify the voltage drop at each light bulb. So the first light bulb, which is 2 ohms of resistance with a current of 2 amps flowing through it, requires 4 volts coming out of this original 24. Now let's take a look at the second light bulb. The second light bulb is 8 volts out of this 24. And then finally, let's look at the third light bulb, and you see that you have the remaining 12 volts available, and now that is the total amount of energy available. Let's just add them up consecutively. So the first bulb by itself required 4 out of the 24 volts. The 2 bulbs required the 12 out of the 24, and there's obviously 12 remaining volts, and then when you get here, you're using all 24 volts that are available to push these electrons through this circuit. Okay, let's move on to the next calculation. In the fourth part of this problem, it's very simple. We're going to find the power dissipation. First for the total circuit, which is PIV, P equals I times V, although you may see here on the reference table in equation E7 that there are 2 alternative forms, I squared times R or V squared over R, but for now we'll just use the first one because it's so much easier and we have that information readily available. So we have a 2 amp draw in this circuit and a 24 volt push, so that gives us a 48 watt power output in our circuit. 48 watts. At home, you use a light bulb in your room. Maybe it's 60 watts. Maybe if you need a brighter bulb, you have 75 watts. Maybe if you really want to light up the room, you use a 100 watt bulb. So here are your watts. And we look at the power at each light bulb in our little sample circuit. 2 amps times the 4 volts used at the first light bulb gave you 8 watts. 2 amps times the 8 volts used at the second light bulb gives you 16 watts. And finally, 2 amps times the 12 volts used in the third light bulb gives you 24. So if you add these back up, 8 plus 16 plus 24, you get back to the 48 watts. So this is a self-checking problem. And believe it or not, that's everything they could ask you about a series circuit as far as the computations are concerned. In closing, we could summarize the series circuit as follows. A series circuit is a circuit that has a battery pushing the electrons through multiple resistors, or light bulbs in this case. There is a total equivalent resistance of all the light bulbs, which allow a total amount of current to get through based on how much resistance each bulb applies. And since each resistance in each bulb may be different, we use a different amount of energy from the battery to pay a toll to get across. We pay that toll to get across, and we add those back up, and we see that it always has to add back up to the battery, which is the conservation of charge, by the way. And then, of course, if we look at the power dissipation, how much wattage is used on each bulb, and we use the PIV formula, and we can find out what the wattage of each bulb would be. So this summarizes the series circuit. I'll see you in the next video for parallel circuits. Thank you for watching.